Hello! I have a problem for you today that is going to be a two-object force problem. So we're doing this with a force analysis, and it's going to have two connected objects. Our problem. Two action figures are tied to opposite ends of a string. The string passes over a pulley, and both action figures hang straight down. The first one has a mass of 50 grams, and the second one has a mass of 100 grams. If they both start at rest, and then are released, they will move. What is the acceleration of their movement, and what is the tension in the string? Alright, so we've got two action figures tied to opposite sides of a string, and then there's a pulley. So, action figure. There we go. Second action figure. Bigger. Okay. They're initially at rest, and then they're released, and then they're going to move. Well, if this one's bigger, I'm going to guess this one's moving down, and this one's moving up. The mass of the first one is 50 grams. Let's convert that right away to our standard unit. And then the mass of the second one is 100 grams, 0.1 kilograms. They start at rest and are released. We want to know what is the acceleration and what is the tension in the string. We're not given a lot of information, are we? All right, two objects. For forces, that means we're going to do two different force diagrams. So let's do number one and then number two. For object number one, action figure number one, what forces act on the action figure? Well, the string is pulling up on the action figure. The earth is pulling down, its weight, and be careful here. We have two different masses. I'm going to remind myself that this is mass number one. Anything else? Nope. This one I'm thinking is going to accelerate upwards. The second action figure, what forces act on that one? Well, the string is holding it up, gravity, so m2g, and now this one I'm guessing is accelerating downward. All right, we are looking for the tension and the acceleration. It's not clear to me what the process is right now, so let's just follow our normal force solving process. We figure out all the forces, break them up into components, add them up, set them equal to mass times acceleration. Well, this one's easy in terms of the components. There's no horizontal component at all. So our XY chart is kind of boring. Nothing. I have a positive t, negative m1g. Same thing over here. So they both accelerate, which means they're both unbalanced, which means the net force, the sum of the forces, has to equal ma. What would that equation look like for these? Well, okay, so we add them up, set them equal to ma. Plus t minus m1g equals, and now this is for the first object, so mass of the first object times acceleration. And then for this one, we still have, well, it's the same force diagram, same chart there, but now it's m2g equals m2a. And you might say, those are identical. How does that help me? The equations, except for the mass, they pretty much cancel each other out. And here's where we have to be careful about directions. This one's accelerating upward. This one's accelerating downward. The value, the magnitude, the absolute value of the acceleration for both of them is equal. I mean, they're tied together. They're accelerating with the same size of acceleration. Just like the tensions are the same. I don't have to have T1 and T2 because it's one string. It's the same tension all the way through. This acceleration, however, going down, we need to take that into account. So I'm going to say that this right here is a negative because that one has a negative acceleration. I'm going to make that look a lot nicer. So the two equations are almost identical, but not quite. We have now two equations, two unknowns. We know the masses, we know gravity, we don't know tension, we don't know acceleration. We're looking for tension and acceleration. So I'm going to write both of these for t equals. So this one becomes t equals m1g plus m1a. This one is going to become T equals M2G minus M2A. All right, so I'm just rewriting those for tension equals, and then I'm going to set the two tensions equal to each other. Because I just said, it's one rope, tension has to equal tension. So let's see, what's this going to give me? M1G plus M1A equals M2G minus M2A. There is one equation with one unknown. We just solved that one pretty easily for getting rid of the tension. All right, and I'm going to clean this up now so I can have more room to do my algebra. So we have equal tensions, so we got rid of the tensions by putting those two equations equal to each other. Now we just have to solve this for our acceleration. And how do we do that? I can get rid of that, give myself some room. So I have an unknown of A. Whenever we have one unknown, we need to get that unknown, all the terms with that unknown over to one side, everything without that term over to the other. So bring all the things with A to the left, all the things without A over to the right. We get M1A, so this one stays over here. That one comes over, becomes positive, plus M2A equals, that one stays over on the other side, M2G, and this one comes over and becomes negative, minus M1G. Those darn subscripts get me every time. So this one comes over, minus M1G. All right, let us factor out an acceleration from this. M1 plus M2. Since I'm factoring, there's a gravity in both of those. M2 minus M1. I want to get A alone, so it's going to be M2 minus M1 times G on this side, and then divide both sides by M1 plus M2. There's a nice little symmetry to that. So it's the difference in the masses times gravity over the combined mass, which in this case is, okay, 100 grams minus 50 grams is 50 grams, 0.05 times G over combined mass, 150 grams over 0.150. And now, if you just punched all these numbers into your calculator, you wouldn't see the prettiness, I don't know what to call it. It's quite beautiful. This turns out to be exactly 1/3 of gravity. When the mass here is double the first mass, the acceleration is 1/3 of gravity. And 3.27 meters per second squared. So there's our acceleration. That's our first one. How do we get our tension? Well, take a look. I have an equation for tension. I have another equation for tension. I like to do both of them because I know that the tensions should be equal, and if I do the math for both of them and they come out differently, I know I've made a mistake. So if I do this, M1 is 0.0509.8 plus 0.05 times the acceleration, which was 3.27. And if we do that, we get 0.653 newtons. All right, let's do this one. This is mass 2, 0.1 times 9.8 minus 0.1 times 3.27. If we do that, we get 0.653 newtons. Ta-da! Okay, so here we have an acceleration of 3.27 meters per second, 3.3 meters per second squared, and we have a tension of 0.65 newtons. So we've answered the question. That's our answer. Not a very big tension, but 50 grams and 100 grams, I'm not going to worry about that. Now before I just walk away from the problem, I want you to predict, what do you think would happen to the acceleration if this one, instead of being twice as heavy, if this one was 4 times as heavy? So if this one was 4 times as heavy as this one, what do you think would happen to the acceleration? So make a quick prediction, and we'll see what we can come up with. So if this one's really heavy now, and this one's only a little bit heavy, what are we going to get? And now I don't have to redo all the physics because I kept everything in variables, which is one of the reasons it's nice to keep things in variables. So if we have m2 as 4 times as big as m1, what is my acceleration? All right, so m2 is 4 times as big as m1. My acceleration is going to be 4m1 minus m1 times g over 4m1 plus m1. That is 3m1 times g over 5m1. Doesn't even matter what the mass is. The masses cancel. And we end up with 3/5 g. So there, our value is 3/5 g, 0.6 g. Oh, darn it, I didn't put that in the calculator. So 0.6 g, it's going to be around 6 meters per second squared. So instead of 1/3 of gravity, now we're up to 3/5 of gravity. We have a bigger acceleration. Is that what you predicted? That if we have more mass here, we would get more acceleration? If so, you were thinking about it right. Now, what are we heading towards? We started off with a pretty small acceleration. Well, I guess I wouldn't call it small. We're getting bigger. What do you think the maximum acceleration would be? And how big do you think the mass difference has to be to get there? Well, the biggest acceleration we could have for something that is just free falling is gravity. But we always will have some little pulling upwards from this one, even if this is really, really heavy. So my guess is it's going to approach gravity, that the biggest acceleration is going to be really close to 9.8, but not quite. Let's see what happens if we do a difference of 10 times? Sure, we can do 10 times. So instead of 50 grams and 100 grams, now, I don't care what the masses are, I'm just going to say m2 is 10 times bigger than m1. Again, I'm just going to go back to this equation. So the acceleration is m2, 10m1 minus m1 times g over m1 plus 10m1. So here the acceleration is 9m1 times gravity over 11m1. So for a 10 times difference, we have 9/11ths of gravity. That's getting pretty big. That's 0.82. Still not all the way up to gravity. What would be a next jump? How about 100? So what if we make the heavy mass 100 times bigger than the lighter mass? See if you can do the math. So now m2 is 100 times bigger than m1. Our acceleration would be 100 m1 minus m1 times g all over m1 plus 100 m1. And if you do that, you get 99 over 101 times gravity, which is 0.98 of gravity. That's pretty darn close to gravity. So if this one, if this was 100 grams, oh, now I'm going to have to do math. This would have to be a kilogram. So 100 grams to a kilogram, 100 times bigger, you would have it almost in free fall. It would behave almost like free fall, just a little bit slower. So that's a 2-object problem, and I wanted to ask some conceptual questions related to it and show you that, hey, yeah, this is approaching a free fall problem once we get the masses to be different enough, a big enough mass difference. So there you go, another 2-object problem. Good job.